All right, today we're going to dive into a high-speed race that's happening all around us, all the time, in a world you can't even see, the world of gases. And it all starts with a question you've probably wondered about at some point. You know, you're at a party, you've got a helium balloon, and one just filled with regular air. Why does the helium one always seem to get droopy and hit the floor so much faster?
Well, the answer isn't some kind of magic. It's pure physics. See, there's a tiny, microscopic race going on, and the winner is decided by the size and weight of individual gas molecules.
To really get what's happening in this race, you have to remember one crucial thing about gas molecules. They never sit still. I mean, they are in constant, chaotic, unbelievably fast motion, just zipping around and bouncing off each other billions of times a second.
Think about it like this. You know that amazing smell of a hot pizza when it enters a room? You don't have to stick your face in the box to smell it. That aroma is actually made of tiny gas molecules that have literally raced from the pizza all the way across the room and straight into your nose. That's the race we're talking about.
Okay, so scientists have a couple of specific terms for how these gases get around: diffusion and effusion. Now, they sound pretty similar, but the difference between them is actually super important. Diffusion, that's our pizza example. It's just the natural tendency for gas molecules to spread out and mix together. They move from where there's a whole bunch of them to where there are fewer until everything's kind of evenly spread out in the room. Effusion, though, that's what's happening with our balloon. It's when a gas escapes through a tiny microscopic little hole, like the pores in the balloon's skin, into another space, like the air outside. So here's the bottom line. Diffusion is all about gases mixing freely, just spreading out. Effusion is a gas leaking out through some kind of barrier. One is spreading, the other is escaping. And it turns out there's a very simple rule that decides how fast this all happens. So, if it's a race, there have to be rules, right? Well, there are, and they're all laid out in a principle called Graham's law, which tells us exactly who's going to win this molecular sprint. Let's hop in the time machine for a sec, back to 1832. There was a Scottish chemist, Thomas Graham, who got really obsessed with this stuff. He just kept measuring how fast different gases could escape through tiny little holes. And he ended up discovering this beautifully simple relationship. Now, the law he wrote down says the rate of effusion is inversely proportional to the square root of its molar mass. Okay, I know, that sounds super dense and sciencey, but what it's really saying is actually incredibly straightforward. That's it. That is the secret sauce. The lighter a gas molecule is, the faster it moves. Simple. Just like in a real race, right? The lightweight competitor, the nimble one, has a huge advantage. And the speed difference can be massive. Take hydrogen, for example. It's super light. It will escape through a hole 4 times faster than a much heavier oxygen molecule. And this brings us right back to our balloon. The helium inside is way lighter than the nitrogen and oxygen in the air outside, so it just bolts out of the balloon's tiny pores much faster. But here's where this story takes a truly wild turn, because this simple little law, lighter gases are faster, was used in one of the most complex and frankly high-stakes engineering projects in all of human history. Yep, the exact same rule that explains why your party balloon deflates was scaled up to separate individual atoms and completely alter the course of the 20th century. So, here was the massive problem they faced. To build an atomic bomb, you need a very specific type of uranium called uranium-235. It's fissile, which is a fancy way of saying it can sustain a nuclear chain reaction. The problem? In natural uranium ore, almost all of it is a slightly heavier, useless type. The good stuff, U-235, makes up less than 1%. They had to find a way to separate them. So, how on earth did they do it? You guessed it, Graham's law. First, they took solid uranium and did some crazy chemistry to turn it into a gas. Then they pumped that gas through a barrier that had millions of microscopic holes. Because the gas molecules with the lighter U-235 were just a tiny bit faster, they would effuse through that barrier a little bit quicker than the heavier ones. But here's the insane part. The weight difference between the two is so small, so the speed difference is also tiny. After one pass through a barrier, the uranium was only enriched by about 0.4%. To get it pure enough, they had to repeat this process thousands upon thousands of times in these enormous buildings called cascades. This whole operation was a core part of the Manhattan Project during World War II, and the engineering hurdles were just staggering. Imagine trying to create huge sheets of material with perfectly uniform, microscopic holes. Then you have to handle this incredibly corrosive gas that wants to eat through everything. And the whole thing used up a mind-boggling amount of electricity.
So why does all this matter today? I mean, it's a great story, but what's the takeaway? Well, it's a pretty powerful reminder of how fundamental science can have absolutely staggering consequences in the real world. This shows us that a basic rule of the universe, something as simple as lighter things move faster, isn't just a boring fact in a textbook. When we really understand these rules and apply a little bit of ingenuity, we can literally change the world.
Now, of course, technology always moves forward. That old gaseous diffusion method was an energy hog. Today, it's pretty much been replaced by way more efficient methods like gas centrifuges, which, by the way, still cleverly use that tiny difference in mass to separate the uranium.
And that kind of leaves us with one last big thought. We just saw how one simple law can connect a deflating balloon all the way to nuclear physics. It really makes you wonder, doesn't it, what other simple, fundamental rules of our universe are just sitting there, waiting for us to figure out how to apply them in ways we can't even imagine yet.